All right, 10.4, I'm going to do number 15 for you. So we were told that we have a circle here, and the equation of that circle is x squared plus y squared equals 25, and that it's rotated about the y-axis to form a sphere. So it's rotated around the y-axis, and it's forming a sphere, so it's a three-dimensional object. And then you have a cylinder that's inscribed in the sphere with its x-axis, with its axis along the y-axis. Okay, so you have basically this cylinder right here, and it was basically a rotation, or I should say like its height is basically along this y-axis. And we're going to write an equation expressing the volume of the cylinder in terms of the sample point. They give us a sample point over here, xy. And we know that any point that's on this circle is going to be basically represented by this equation. And I can use this equation to solve for one of my variables. That way I can plug it in. But let's think about that later. So the next thing we should probably look at is the fact that this thing has a radius, right? So each of the bases, I know I've done a terrible drawing here, but each of our bases are circles in a cylinder. And so each base has a radius, and those radii will be equal. And that radius is actually represented by x. And then the cylinder also has a height, and that height is along the y-axis. Okay, now half of the height is going to go from the x-axis up to the value y, whatever that y value is. So if I want the entire height of this, I'm going to have to double that. All right, so let me just write that. Let's see, I'm going to write that over here. So your height is really going to be 2 y's, and your radius is really going to be x. Now, how do I find the volume of a cylinder? Okay, well, the volume of a cylinder is basically the area of the base, which our bases are circles, so pi r squared, times our height. Well, in this case, our radius is not going to be r, it's going to be x. And in this case, our height is not going to be h, it's going to be y. But we have to double that, because if I just take this point right here, that height, right, is just going from the x-axis up. Okay? So, and that's how all of our y values work, right? Any y value on any graph is always either from the x value to the top, or the x value, or the x-axis to the top, x-axis to the bottom. Okay, so instead of h, I'm going to use my 2y. Now, problem is we need just one variable, and let's see, it says write an expression expressing the volume in terms of the sample point. Plot the volume of the cylinder as a function of x. As a function of x means I shouldn't have any y's in there. I've got too many variables. I got v, I got x, I got y. If it wants it as a function of x, your input is going to be x. So I'm going to come back up here, and I'm going to solve for y. So I'll just subtract x squared to the other side. Oops. Let me go 25 minus x squared. And then y will equal, now normally when you take the square root of both sides, and you're taking the square root of an unknown, you'd have positive or negative, but that really wouldn't make any sense for height. We just need the positive. So I'm just going to do the square root of 25 minus, minus x squared. Now some of you guys get really excited here and you're like, oh yeah, that's 5 minus x then. You can't do that. You can't take the square root of this and get 5 minus x. Just like you can't take, well, if I factored this out, so here's just a little side lesson here. If I factor this out, that's really the square root of 5 minus x times 5 plus x. There's no perfect square in there, right? This really becomes that. Does that make sense? Hopefully, because I've seen a lot of mistakes here. All right, so I'm going to use that, and I'm going to plug that value of y that's in terms of x. I'm going to plug that right in here. So I'm going to do volume is really I think I'll bring the 2 out in front. 2 pi times x squared times the square root of 25 minus x squared. I now have an equation for the volume of the cylinder in terms of x. And now what I do is I look for my maximum. Oh, excuse me. This would be really hard for me to figure out the maximum on my own, so I'm going to use my graphing calculator. So I'm going to go, let's see, 2 pi x squared square root of 25 minus x squared. We should be good to go. Now I'm going to go ahead and graph this. Let's see. I don't think I'm going to be in the right window, but let's just see what I end up getting. Oh yeah, I need to go way, way higher. I also don't need any negative radius or radii, so I don't need any negative x values. And let's see, it's like plugging in x, I don't know, it looked like, you know, x being 2. So right there, that's going to be for 8 pi, and let's just say that that ends up being, I don't know, 5, so 24. It's going to be in the hundreds. So let's try my x min. I'm going to go way smaller. Let's just go like -2 so I can still see the x-axis. My x max, I don't think I need to go any bigger because, you know, the maximum looked like it was around 2 or something like that. Maybe 4, who knows. My y max, I said I was going to go into the hundreds, so let me just try that. Not quite high enough. I'm going to go a little bit higher then. So yeah, the max actually was probably going to be a little bit more over here, which would make sense why I didn't get such a accurate number there. Let's go 400 and see what happens. There we go. Okay, so now I'm going to calculate where my max is. So about 4.082. And that will give me a y value, or in this case, a volume of 302.3 because it goes 2998. All right, so let's see. Find the value of x that gives the maximum volume and find the maximum volume. Okay, so the maximum x value, let's see, do we have any units here? I don't think so. So this is going to be our radius that gives the maximum volume, and then this is going to be our maximum volume. And again, I used my grapher to figure out that maximum. Okay, I'm going to also do number 17 with you guys. So my drawings are just getting worse and worse. But basically, once again, I have the exact same sphere, which was created by rotating this circle about the y-axis. Here's our y-axis. And within that sphere, I have a cylinder. And that cylinder has a point on the sphere. And that circle that was created is represented by this equation. And in our last problem, number 15, we were able to solve this for one of our variables so that we could have everything in terms of x. So when we solved this, we got y equals the square root of 25 minus x squared. So now we have basically y in terms of x, so we don't have to use too many equations. All right, so 17 basically says you have the exact same sphere and cylinder as in problem 15. And then it asks us to find the radius and altitude of the cylinder with maximum lateral area. So what is lateral area? Well, lateral area is if you think about this cylinder, maybe for example, it's a water tank. I ride my bike a lot. I go up to this water tank that's near my house. So that's kind of where my brain is right now. So this water tank needs to be painted, right? It needs the outside, the exterior, maybe got some graffiti on it or something. It needs to be painted, okay? So that would be the lateral area. How much paint's it going to take to paint the exterior of this water tank? You probably don't want to paint the interior because you might get some bad chemicals in your water. Okay, so that's lateral area. So when you think about lateral area, it's not the same as volume. Volume, we took the area of the base because we would fill up this base, and then we would fill it all the way up to the top, right? So that's basically area of the base times the height. Lateral area is different. We want the outside. What's the outside of a circle? Well, that's the distance around a circle. The distance around a circle is circumference. So for lateral area, you're going to take the circumference, which is 2 pi r, and you're going to multiply that by the height now. Well, as we did in problem 15, our radius is really our x value, right? Because if you think about drawing a radii here, that's really going to be whatever the x value is. And then if we think about our height, well, our height from the x-axis up is y. From the x-axis down, it's another y, even though I know my picture looks terrible. And you're probably saying to yourself, it would be negative y. Well, of course it would be negative y if we don't put this in context. But if you put this in context, the height needs to be positive. Okay, so from the x-axis up is a positive y. From the x-axis down, you just double that positive y. So your height then is 2y. So then our lateral area is really 2 pi x times 2y. And just like we did in our last problem, we're going to take this value of y and we're going to plug it in so everything's in terms of x. So now our lateral area is really 2 pi x times 2 times the square root of 25 minus x squared. Or to make this a little bit more simple in my calculator, I might multiply the 2's. So I get 4 pi x square root of 25 minus x squared. Okay, so now we're looking for the radius and the altitude of the cylinder with the maximum lateral area. Well, I'm going to, so this might be helpful because we've got a lot of stuff we've got to think about. So when I graph this function, my output is the lateral area, my input is my x, or in other words, that's my radius. Okay, so putting this into my graphing calculator, I think I'm going to put 4 pi, let's see if I waste time doing this, 4 pi x, 25, nope, that worked out really well. So now I'm going to graph that. Let's see if my window's good. Oh, my window's pretty good. Okay, so I have some thing that looks something like, I don't know, like this. I want to figure out where my maximum is, so I'm going to calculate my max. So this maximum is happening when x is 3.536 approximately, and this point is 157.08. All right, so I get a maximum radius, or sorry, I get a maximum lateral area when my radius is 3.536. Okay, so I know that my radius has to equal, I should say approximately 3.536. So I found the radius, which is my x value. And then I need the altitude of the cylinder with the maximum lateral area. Well, the altitude is really just the height, right? And so my height here, we found an expression for that, or an equation, which is our y value, which is the square root of 25 minus x squared. And we have to double that. Our altitude is going to be double that. I've gone over that already. Okay, so the altitude here is the same as the height. Oops, I don't know how to spell height. And that's basically, remember, we decided that our height was 2 times y. Well, y is actually that, so I'm going to say that's the same as 2 times the square root of 25 minus x squared. And then I need to actually take my x value. There's my x value. I'm going to plug that in so I can get that. And it's approximately. I did something wrong. Let's go back to this. I think I was supposed to square that, right? Because it's x squared. Yep, that's the problem. So we'll square that. There it is. 7.070. So approximately 7.07 is going to be your altitude or your height. I like to call it height. Okay, I think I just answered A. This is one of those problems where you got A, B, C, D. Oh, it only goes to D, so that's pretty nice. All right, B. Find the radius and altitude of the cylinder with the maximum total area. So in your notes, just as a reminder, lateral area for a cylinder was that 2 pi r times height, which is basically the circumference times the height. So that's the lateral area. We don't include the bases. But the total area now, which they like to call the S for surface area, is basically the lateral area plus the area of the two bases. So you got 2 times the area of one of the bases. So total area just includes the bases. All right, so I am finding the maximum total area. So basically what I'm going to do is I'm going to take my lateral area, which was this equation, and I'm going to add the area of the two bases. So total area basically is your lateral area plus area of two bases. Okay, so let's see, we'll call it S, just like they do for surface area. And my lateral area equation was 4 pi x times the square root of 25 minus x squared. And then we need the area of one of these bases. Okay, well, we said that, this is going to be pi r squared. But instead of r, I'm using x. So it's pi x squared, and there's 2 of them. And everything is in terms of x, so I think I'm good there. I'm going to go ahead and use my graphing calculator to find the maximum total area in this situation. 1 second. So I'm just going to take that exact same thing, lucky me, and then add to it 2 pi x squared. Okay, so I can see that I have this graph. It's interesting that it stops at some point. But let's go ahead and find our maximum. And I'll go ahead and I'll graph this so that we have an understanding. This is my surface area. This is my x, which is really my radius. And it looks something like this. And let's see if I can figure out where my maximum is. Okay, so it appears to me that it's at like 4.253. And the maximum is actually 254.162. Okay, back to my question. Find the radius and altitude of the cylinder. Okay, so my radius, well, that's this value. 4.253. And then the altitude, though, we've got to go back, and we have an equation for the altitude. If you remember from the last one, it was 2y, right? Our height is 2 double the height, double our y value because we want double the height, which we've gone over now several times. So our height is actually going to be 2 times the square root of 25 minus x squared. So going back into my calculator, And I'll just take this exact same equation. I'm just going to replace this number with 4.253. That should work. And I get 5.258. All right, let's see next. Does the cylinder with maximum lateral area also have the maximum total area? Well, those cylinders are totally different, right? This cylinder has a radius of 4.253, and this one has a radius of 3.536, so they are not the same. I'll put the radii are different, as are the altitudes, right? I should say the radii are different as well as altitudes. Or I'll put height. Okay, does the cylinder with maximum total area also have maximum volume as found in problem 15? So if we go back to problem 15, that one had a radius of 4.08 and a volume of, well, that doesn't matter, but a radius of 4.082. This one was 4.253. So note, different radii. Okay, and now number 19. So now we see that our cylinder is on its side. So instead of its radius being an x value, we can see that if we go up along, or those, go basically from the x-axis out to the side of this cylinder, we're parallel to the y-axis. So the radius now is actually going to be our y value. And our height now, we can see that our height basically goes from the y-axis all the way out here to whatever x value is given to us. Now, the height is just along the positive x-axis. This, we used quadrant 1, and then I think that's what it said. Let me reread that. Yeah, it was rotated about the x-axis, the right half of this ellipse. So basically, well, and in the picture you can see, we basically are just using the positive side of the x-axis. So our height here is just going to be x. All right, well, I didn't read the problem for you. This is actually kind of a good problem. The bow of a submarine has the shape of the half ellipsoid formed by rotating about the x-axis, the right half of the ellipse. And the ellipse is represented by this equation right here, where x and y are length in feet. The ellipsoid, a doubly curved surface, is to be shaped from thin metal that is relatively easy to mold. The pressure hull, made of thick metal, is in the form of a cylinder. So this right here is the pressure hull, inscribed in the ellipsoid. How should the cylinder be constructed to give it the maximum volume? So we want to maximize the volume of the cylinder. And then after that, we'll answer the second question. So you can see where this is like a real world problem to basically engineer and design and then build a submarine. All right, so we want maximum volume. So once again, volume of a cylinder. And if you've forgotten any of these things, they're all right here. So a volume of a cylinder is basically you take the area of the base, which is pi r squared, and you multiply it by the height. Okay, so the volume here is just pi r squared times height. But instead of r, well, our radius is y. And instead of height being h, we're going to use x for that. So then we can turn everything into one variable. It doesn't tell us what to do. We could either put everything in terms of x or everything in terms of y. I'm going to go ahead and put everything in terms of x. So I'm going to come back up here to this equation, and I'm going to solve for y in terms of x. So I know that I'll have 900 y squared equals 202,500 minus that 225x squared. divide everything by 900. Taking the square root of both sides. And I could put, I'm allowed to take the square root of 900 because it's like taking the square root of the numerator, taking the square root of the denominator. So I'm just going to put this all over 30, I believe, is the square root of 900. Okay, so now I'll take that y value, and I'm going to plug it in right here. So now I have a function for my volume, which I can then graph and come up with my maximum. Yeah, I guess I can't really use any of this, so I'm just going to go ahead and clear it. I think I got it. Let's see what we got going on here. Ooh, definitely not tall enough. Let's go to 1,000. Oh, still not big enough. I think I'm also going to change. No, let's keep going. Window. Let's put 2,000. I have no idea. Oh, man. I'm not doing so good on this. I'm going to also change my X max. I'm going to go up to 20 and maybe make this 4,000. Still not tall enough. 10,000. Come on. Oh, finally. It looks like I'm almost at the max. Or I'm a little bit past it. I'm going to go a little bit more past it. Okay, so now I can actually see the peak. Okay, so this is our volume. That would be feet cubed. And then going through here, looks something like this. Let's just pretend like that's right. And this is our x, and our x is actually our height, right? And these are just in feet. Okay, so finding my max. All right, so I got an X max of 17.321 and a volume of 8,162.097. Okay, back to my question. How should the cylinder be constructed to give it the maximum volume? All right, so we have a maximum volume of that. The height should be 17. So height will be approximately 17.321 feet. So then we also need to know what the radius should be. And remember, our radius was represented by this function. So we'll go back in there and put that in. So we're going to do the square root I'll do that and then I'll divide by 30. I got 12.247. All right, now there's one more question here. How much of the heavy steel plate will be needed to form the curved walls of the cylinder? Okay, so we just talked about the volume, but the curved walls of the cylinder, so once again, just looking at, this part right here. So how much steel needs to be used in order to create these curved walls? All right, so the curved walls are basically your lateral area. So that's the same as taking the circumference of the base and multiplying it by the height. So curved walls is the same as your lateral area. And this is basically going to be the circumference of the base times the height. And again, our radius, we're using y for our radius here, and our height is being represented by x. So really, this is 2 pi times y times x. Okay, and we came up with some values for each of these. So let's see here. Our radius was really 12.247. So this right here is going to be our y. And our height was really our x. So we just plug those numbers in. And when you do that, this is an approximation because I rounded those. You're going to have 1,332.85 square feet needed of heavy plate steel.